recording, but I am simply assuming everybody has to consent anyway. Okay. So now that we are recording, let me just start with what the original question was. I think this question refers to this issue of the Z parameter network calculation. So before we go on to the specific thing about the Wheatstone bridge calculation that we talked about, are there any questions about the method itself?
Yes, sir. Sir, another question is, you said that the two components on either side of the network inside the black box, like no current flows through them. So I'm not sure how the current in one part controls the voltage or the current in another part. Like,
Okay. Okay. I guess let me just try to paraphrase the question. I hope I have understood the question again, right? So first of all, the idea is, okay, let me just start sharing my screen. And let me also switch off my camera. It's going to make the recording slightly smaller. You have all seen my face enough, I guess. Let me just share the screen now. And the customary question that's always asked now is, I hope you can see that I'm presenting to everyone. In case any one of you are not seeing that, that means you have pinned somebody else. Okay, either unpin that person or just pin my presentation. In that case, of course, you are only going to see my presentation all the time. Okay, so let me just write this down. The basic idea behind this two-port network theorems, as expected, now my son has a lot of pens. I'm betting none of them right, but this one does. So there's this black box inside which there's a mess of circuitry which I don't know about, or at least I pretend that I don't know what's inside. Okay. And this is a two-port network because there are two ports. One port on the one side, which we label port 1 or port input. And the other port is labeled port 2 or output. Strictly speaking, 1 and 2 is better than I or I and O, for the simple reason that you may be using this in a situation where the input-output words make really no sense. But still, you have two ports. One you are going to designate as input, the other as output. Okay. And what I said was something like this. You can replace this with an effective circuit, which essentially follows from this Taylor series. And you can replace this with something which looks like this. By the way, in the first video, there is video number 3, the circuit components have been drawn slightly wrongly, in the sense that the standard notation for a control source, at least in the American system, are diamonds. So round circles are usually used for voltage sources or current sources. The current source is supposed to have an arrow. The voltage source just has minus and plus signs. But these are actually usually typical American style symbols for constant sources and not controlled sources. Controlled sources have diamond shapes. So this one, the one on the left here is a voltage source, a controlled voltage source. And the one on the right is a controlled current source. So because I was not paying very much paying attention to the software that was used to create those presentations, I messed that up a bit. Lecture 3 has those symbols wrong. Anyway, be that as it may, it should be easy to understand what's being talked about. So you have a voltage source in series with a resistance on one side and a similar thing on the other side. This, remember, is an effective model, not what is really inside. Okay. So I am not saying that the input and output on your actual two-port network is not connected. They are definitely connected. And there's a mess of circuitry inside, and that mess of circuitry is what is causing the voltage of the input to affect the output. Okay. So in reality, there are connections between input and output. What I'm saying here is not a statement about the actual circuit. It's a statement about this effective circuit. In the case of the effective circuit, the input voltage V1 is Z11 I1 plus Z12 I2. This is nothing but a statement about the Taylor series expansion of the formula. Okay, nothing other than that. Similarly, V2 is Z21 I1 plus Z22 I2 is also Taylor series carried out to the first order. So these are two mathematical equations, and you could just deal with these mathematical equations when you do any calculation. You did not need a circuit. The reason for changing this into a circuit equation, into an effective circuit, is that if you have an effective circuit, you can actually do a lot of nice calculations where you can use all these circuit theory ideas. Like when resistances are in series, they add. When they're in parallel, you have this R1, R2 by R1 plus R2 formula. All these easy things you can use. Okay. So basically what you have is a circuit which looks like this. This circuit, I hope everybody understood that. Let me just make this a bit more clear, I hope. Yeah. The equation that you have is simply V1 is Z11 I1 plus Z12 I2, right? And so because this is a voltage which is the sum of two voltages, it has to be effectively a series circuit, out of which Z11 I1 can be easily obtained as a drop across an impedance Z11 if a current I1 is flowing through it. So to get the Z11 I1 term, all you need is this series impedance. However, the other term you simply cannot get by putting an impedance, for the simple reason that this voltage depends not on the current flowing through this input, but through some other place. So Z12 I2 has to be written down as, okay, once again I made the same mistake, as a current controlled voltage source. Current controlled because I2, the value of I2 is controlling it, and it's a voltage source. It produces a voltage given by Z12 I2. Okay, so this part of the circuit simply models this equation. There's nothing else to it. Okay. Similarly, the other part is simply modeled by Z22 and Z21 I1. Okay, so these are just effective circuits which model the two equations that we have. Now, if you look at these two equations, how is it that the input is connected to the output? Via the fact that there are control sources. Okay, right? In the real circuit, the input is connected to the output via wires with components and other things, which means that the input and the output affect each other. Here, the effective modeling of that is done by a single current controlled voltage source connected to the input, where the voltage is controlled by the output current. And similarly, on the output side, there is a current controlled voltage source where the voltage is controlled by the input current. So the effect of the real circuit components which connect the input and the output is being modeled here effectively by these two pieces. Okay. So I'm not saying that the input and the output are not connected in the black box. They are definitely connected. That's how the input and output affect each other. However, effectively what happens is, as far as small signals are concerned, small v1 is simply Z11 I1 plus Z12 I2, which is something you can model with just these two components. And you don't really need anything else. This is enough to model this equation. Similarly, this one is enough to model the other equation. Okay. So when I draw the equivalent circuit, okay, this is very much like in the Thevenin theorem. We said that we model whatever is going on inside this one port network by a voltage source in series with a resistance, right? What is going on inside may be very complicated. Doesn't matter. The theorem says ultimately it's all something you can model with a voltage source in series with a resistance, as long as you're dealing with small signals. Okay, that's because, of course, you're using Thevenin's. In both cases, you're using Taylor series, and you're using only the first order terms in the Taylor series, not the higher order terms. So higher order terms will, of course, make this more complicated. In most situations, especially if these are linear circuit components, there are really no higher order terms. So this, in a sense, is exact. And even for nonlinear circuit elements, usually for small signal operations, the higher order terms are insignificant. Not always. In fact, there's one very important application of electronics where higher order terms become very important, which is where you say, when you use those electronic amplifiers to produce distortion and call it music. I'm not very sure whether everybody calls it music, but most of electronic music nowadays, most of it, at least most of the high voltage, okay, that's a bad word to use, but most of the high amplitude metal sounds, etc., they depend on the fact that nonlinear effects distort sound. And to some people, at least, those distortions are musical. But right now, we are talking of only linear effects. And so you could just draw these two pieces entirely independent of each other with no connection. What I said in the lecture was you could draw a wire here. That wire serves no purpose. If you think of this as this effective circuit and this effective circuit, then easily show no current will at all flow through this wire. So, but what this wire does is that it sort of tells you that there is a connection between input and output. Of course, the circuit already tells you that. It tells you that indirectly via the fact that the voltage source here is not dependent on the current coming in the input, but it depends on the current coming from the output. Okay, so you could model it with the wire, without the wire, doesn't matter. The wire is simply usually drawn so that people can keep in mind that the input and output are really connected and they are not disjoint from each other. Okay, so does that answer the question?
Yes.
So this is really more of a pretense. That wire is, whether you draw it or not, doesn't matter. It's usually drawn by convention. Okay, any further questions? And in case people have been chatting, I can't see. Okay, no other chat. So,
sir.
Yeah. So just identify yourself. I don't know all your voices yet.
I'm Rahul.
Okay.
So what I was asking is, like in the third lecture, when we parameters, you like assume for the parameters we we take input open or output open depending on the parameter. But what so we are actually setting the small I1 and small I2 to 0, right? But small I1 and small I2 are fluctuations and not the actual value of the current.
Exactly. I did say that in the lecture itself, in case you missed it.
Yeah, but when you're solving the problem, you have like the example you gave at the end, you just took the entire output to be open.
That's a good point. I should have clarified that. In usual circuit applications, in situations, I was anticipating the situation where we would actually use it. Okay, we will actually use this in a big way to analyze, say, transistor circuits or even diode circuits, but mostly transistor circuits or other circuits like that. Okay, now in such circuits, in order to make the system work properly, you have to provide a bias. That is, you have to provide some voltage and current to begin with, and you make your signal produce a fluctuation across that. We did talk about that in the lecture a bit at the beginning as a motivation, but we did not go into details because that, of course, is going to come later when we talk of transistor circuits. So usually there are bias voltages and currents, and fluctuations around that are what we are considering. So when I say I1 equals 0 or small I1 equals 0, actually means output open, or sorry, input open. I don't really mean that the input is open. I mean the input capital I1 current is held constant. Okay, that's, I guess, what you are saying. Or when I say small I2 equals 0, I really don't mean that the output is open circuit. What I mean is capital I2 is constant. However, the circuit that I solved at the end, the Wheatstone bridge, that has no biases or nothing biasing the circuit ab initio, right? There is the only voltage source is the voltage source I connect from outside. What that means is in this case, capital I1, capital I2, or capital I1 0, capital I2 0, the values from which we were considering fluctuations, but actually 0. There is nothing to begin with. So there open means really open, or short means really short. Is that okay?
Oh, okay. Yeah, sure.
However, you're right. So when I say input open, I actually mean AC open. That's the terminology we use. AC open essentially means, look, if you have a transistor circuit, you need an average bias current or voltage to flow through the circuit. Without it, it will not work. Okay. So if I suddenly say that, well, I just switch off my source completely, that is, I open out the input, then what would happen is even the bias voltage will also go to 0, or bias current will go to 0, which will simply mean my circuit will not work. Okay. So when I say input open in those contexts, I would usually mean that the input voltage is fixed at a steady value, it's not changing. We are going to see this AC analysis very often soon, and then this terminology will become sort of obvious to you. Although you're right, the terminology actually is to be used carefully. When I say open, I mean AC open. That means no fluctuations. Okay, Arnab has asked a question. In Norton's method, you ignore the battery source between two nodes when you calculate the net current passing through these nodes. So why do you assume that the battery source between these two nodes doesn't give extra current? I guess I'm guessing here, but I'm pretty sure that this is in context with the practice problem that I had given. Okay? Is that right, Arnab?
Yes, sir. It's in the practice problem
Yes, the
that you
solution
have
that I
given.
gave for the practice problem, right? Okay, there it was essentially something like this. You had a lot of branches with something happening here, some currents coming in. Then there was a battery. And then there was some other node. And this happened to be a particularly bad problem for Norton's method. That was not deliberate, it just turned out to be that way. That some of the nodes had fixed voltages, but other you could not write down a standard Norton-like equation for any one of them. So what I did was I said the current flowing in through this in this node has to be equal to current flowing out through this wire. Okay. So Arnab is asking, because there's a battery in the middle, why can't the battery produce extra current? Right? Is that the question?
Yeah.
What I see
Yeah,
is some
sir. It's
I1, I2, I3. I don't remember the exact values, but these are say I4, I5, I6. Of course, if they had all been joined at a single node, then I'm pretty sure nobody would have doubted that I1 plus I2 plus I3 equals I4 plus I5 plus I6, right? If the battery had not been there, I'm pretty sure nobody would have had a question about this. Even if there was just a short here, right? But now notice how much is the current coming into this node, the node below? That's I1 plus I2 plus I3, right? How much current must leave this one? I1 plus I2 plus I3, right? Does Kirchhoff's current law apply to this node? How much current must flow here? Must be the same. Is that okay? Because there's no other place for the current to go. So this current has to be the same as this current, which means that is the one which has to branch out into I4, I5, I6. Now, in this context, the real question is, isn't the poor battery doing anything? It's getting current I1 plus I2 plus I3 from one end and sending the current right through. Then why need a battery at all? So what is the job of the battery? Can anybody tell me that? By the way, even if you have a circuit much simpler circuit like this, you have a current I on this side, The same current comes in on the other side, right? There you don't ask the question if battery is getting current I on the negative side and pushing current I out from the positive side, then why isn't it producing any extra current? The real job of the battery is not to produce extra current. The real job of the battery is to keep the current moving and produce a potential difference between the two ends. Notice that, okay, for the timing, let's just pretend that current is produced by positive charges. You all know it's not, but let's just pretend that there are positive charge carriers in our world and that's what causing the current. So what the battery does is that it pushes those positive charges along the wire. It comes all the way back down here. But by the time it has come back to the negative end, the positive charge has lost all its energy. So it cannot make its way back to the positive end. Unless the battery does something, the battery produces the energy which makes it go from the negative end to the positive end. Okay, so just a quick poll here. Current always flows from higher potential to lower potential. Is that correct? So I want you to answer. Anybody?
So outside the battery.
Well, outside the battery. What happens in a battery? That actually is perfectly correct. Well, partially correct, not perfectly correct. In the sense that through all passive components, current flows from higher potential to lower potential. When I say passive component, I mean something which does not produce energy of its own. It is obvious from Kirchhoff's voltage law, for example, that it's impossible for current to always flow from higher to lower potential, right? Because it's flowing, right? If it keeps on flowing from higher to lower potential all the time, then what will happen? Then it will just ultimately keep on flowing to lower potential, lower potential, lower potential. By the time it comes back to its original position, it will have ended up at a lower value, which can't happen, right? Because the whole idea of KVL is when you come back to the original position, potential must be the same. So current cannot always flow from higher to lower potential. It has to sometimes flow from lower to higher. But to flow, for current to flow from lower to higher potential takes energy. Okay? And this extra energy has to come from somewhere. Clear? And this extra energy is provided by the power sources. Could be by a battery or could be some other power source. But it has to be a power source. If there's no source of power, it's impossible for current to flow from lower to higher potential. Okay? So, is that clear? So the context essentially is the battery's job in this particular case is to produce the potential difference between the two ends. Its job is not to produce extra current. Battery never produces extra current. Some current comes in the negative terminal. It makes that current climb up a potential barrier and go out from positive terminal. Okay, any further questions?
So,
Yeah.
regarding the question I asked first, like what would be the answer? I'm still not understanding.
What was the
Why is the flux? Sir, I asked that if the voltage source, external voltage source outside the Wheatstone bridge is connected, so that is constant, right? So I am not understanding how the fluctuation works here. You wrote down the equations in terms
Here
of
the fluctuation. Wait a minute. Here, I actually answered this question in answer to another question. Here, the current and voltage at steady state. You have to understand what the quiescent point value is. Quiescent point
Yes,
or one value is when you don't connect a signal, what's happening to the circuit. Okay. For the Wheatstone bridge, that terminology and that explanation or that whole technology will be useful when we talk about circuits which require a bias voltage and current, and you have produced additional say signals to make the thing work. That's essentially in anticipation for amplifiers. Unfortunately, we have not studied enough amplifier theory to give that as an example. So I gave a very simple example, that of a Wheatstone bridge. can use it anywhere, but in a Wheatstone bridge, how much is the voltage and current when there's no signal? The answer is 0.
Yes.
Okay. Or rather, you might even say the battery is producing the entire signal. That's one way of looking at it. The other way of looking at it is simply because the circuit is linear, I don't even need to talk about small fluctuations. Whatever voltage I give, starting from a quiescent value of 0. So for that circuit, the quiescent point value is 0. That's important. And I don't really need a small signal here because the circuit is a linear circuit. And because it's a linear circuit, its quiescent point value is unimportant. Or rather, size of the signal is unimportant. No matter how big the signal is, V1 will still be Z11 I1 plus Z12 I2 exactly. That's because we are dealing with a linear circuit, a circuit where all the components have voltage versus current as a straight line. If I say diode in the circuit, where voltage and current are non-linearly related, any non-ohmic conductor, then of course this will not be exact. It will be only exact for small fluctuations. Is that okay?
Yes.
Okay. Next question, if any. Okay, I can see. So how to deal with Maxwell's loop method when there's a pure current source? There's zero internal admittance and cannot be converted to equivalent voltage source. Well, as I said, Thevenin's theory, this Maxwell's method. Let's draw a situation like this. Suppose I have a pure current source, I, and then I have resistances R1, R2, and some voltage sources somewhere, let's say R3. And I want to use Maxwell's method, loop method. Okay, so let's put in the loop currents I1 and I2 here. So I can immediately write down the loop equation for the first loop, which will be I1 into R1 plus R2 minus R1 I2, right? That's the way in which you write down loop equations. You multiply the net resistance in the loop by the current of the loop minus IR terms for the adjoining currents. And that has to be equal to the net voltage rise. Here, of course, is a drop, right? Because when I'm going around like this, I'm going from the positive end of the battery, the longer end, to the shorter end, which is the negative end. So this is equal to minus C. That's one loop equation done. Unfortunately, I cannot write down a loop equation for the second loop. Why? Because while I can write down I1 R1 plus R2, sorry, I2 R1 plus R2 minus I1 R2 as a drop across R1 and R2, but these two together has to be equal to the rise across the current source, whatever rise is here. This has to be correct. This is Kirchhoff's voltage law. The only problem is when you're crossing a current source I do not know what the voltage drop across it is going to be, because the voltage drop across it could be anything. That's exactly what a current source is. It produces the current I. That's it. No matter how much the voltage source is. Of course, in this particular circuit, the one I've drawn, there's a way out, which is I is in series with R3. So that's a current source in series with the resistance. Okay, there is no way out. Sorry, I made a mistake. If I had been in parallel with the resistance, I could have just converted that into a voltage source. Here I can't, because I is not in parallel with the resistance. Okay. However, in this particular case, the solution is very easy, because it simply tells you that I2 has to be equal to I. Right? Why? Because I2 is the current flowing in the loop, and here, as it stands, there is nothing else. So the current I2 is flowing through I, flowing here, and that's exactly what the current source does. The current source produces current I through it. So here I2 has to be the same as I. Of course, if this had been a part of some other bigger circuit, maybe one more loop here and I had put in I3 here, then the equation would have been I2 minus I3 equals I. Whatever be the case, the current source essentially produces a relationship between the mesh currents. Okay. So ultimately, you get as many equations as you need, but you don't get them directly in the same standard way. Just like, well, you have a standard method for writing down the mesh equations. That works fine as long as you don't have pure current sources. But the pure current sources essentially give you direct relationships among currents. Like if you did not have this loop, then the relationship would have been a very simple one. I2 would have been equal to I. So I would have two equations. There are two mesh currents, I1 and I2. One equation I already have between them, which is I1 into R1 plus R2 minus R1 I2 is minus E. That's one equation. The other equation would have been this very simple one. I2 is I. Okay. So this is how it essentially goes. And right now, the way I've drawn this circuit with the third loop, you might have noticed that I actually seem to get only two equations, right? One equation, which is I1 R1 plus R2 minus R1 I2 is equal to minus E. The other equation, which is this one. Of course, I don't have this because that was the case when there was no third loop. But I do need one more equation. Say, if I label these as R4, R5, R6, remember, I cannot write down an equation directly for this loop. Neither can I write down an equation directly for this loop, because in both cases, there's a current source sitting in the loop, which will have this problem that I don't know what the voltage drop across the current source is. So how would you solve this problem using the mesh method?
Sir, then I will apply the loop method for the bigger loop.
Okay, in this case, there are two answers. One is you will just use the loop method for this loop. The only problem with using the using KVL is that when you're crossing a current source, you don't know what is the voltage drop across the current source. As long as you don't cross the current source, you're fine. That's one way. In fact, that's exactly what we did in the practice problem for Norton's method also. There we had a voltage source, and if we cross a voltage source, we do not know how much current is going to flow through it. So I couldn't, or how much current is driving. So I could not use that directly. But I just used KCL, but had to work a bit harder at that. Here, you could just say I could write this loop equation with this unknown voltage here. Another loop equation again with this unknown voltage here, but it's the same unknown voltage. Because it's the same unknown voltage, you could eliminate the two and get an equation. Or you could take the bigger loop, which is essentially going to give you the same result. In this particular case, I hope it's not too messy, so messy that you can't make out what I'm saying. But there was another simpler solution. Can anybody point that out? This bigger loop will definitely work. But there was a simpler way out in this particular case. Can anybody point out what that was? Why was the current source a problem here? Because
the left loop can be considered to be admittance for, and it can be
exactly
the total can be considered.
So what is being said here is you could simply think of this whole R4 plus R5 plus R6 thing as an resistance, not really an admittance, but it's a resistance whose admittance is of course 1 over R4 plus R5 plus R6, and that's in parallel with I. So I could just convert the I parallel with R4 plus R5 plus R6 combination in this particular case into a voltage source and then start with it. Okay. I hope everybody knows how to identify series and parallel, right? That may sound like a rather nasty thing to say for students at this stage, but I have found that very often people can't really figure out series and parallel properly. And not just students, quite a few, well, let's not name people, but quite a few eminent so-called scientists have difficulty in figuring out whether circuits are in series or in parallel. The standard rule is very simple. Series means same current must flow through them, no branching, no branches available. Or if there's a branch, somehow that branch does not have a current through it, somehow. Okay. Parallel simply means both ends must be joined together in such a way that the voltage across both must be the same. That's very simple. However, in a complicated circuit, very often it becomes difficult to figure out which ones are in series and which ones are in parallel. So you have to clearly look for, is there any branch by which current can be diverted? Or is there a way of having a voltage drop? For example, in this rather messy thing which I have here, which I'm pretty sure nobody can see now, but we had an I, okay, let me just draw it again. We had a current source I here, a resistance R here, say whatever I called it R3. But this I and this R3 were in series, of course, as it stands, same current going through them, but not in parallel, because the voltage drop across this and the voltage drop across this, they're not the same because there's a resistance in between and there's a voltage drop between the two ends of that resistance. In this particular case, it was easy to identify, but very often in a complicated circuit, that may be difficult to identify. So please pay attention to that when you're analyzing a circuit. Okay, further questions? By the way, I'm seeing, since YouTube tells me how long the videos have been watched, I see that many of you have not watched the third video yet. At least not the full video, because the simple multiplication, if I multiply the number of students in this class by the duration of the video, I should be able to figure out whether everybody has watched the whole video or not. I'm not even talking about the fourth video, but even the third one. Well, even the second one, I'm not sure everybody has watched the whole thing. But remember, these are classes and you have to watch the whole thing because that's how the class is going to proceed. And of course, because it's there on YouTube, you may feel that you will watch it at your own leisure and so on. But if you leave it for later, it's only going to pile up. Because there will be others as well, right? So it's best to utilize the time slots that are given to watch those videos at least once. Then you can always come back to it later. That's one advantage of having a video. Because if you don't do that, then the scheduling for the entire discussion sessions, etc., becomes difficult. And for example, there should have been a huge number of questions from the two-port networks, because this is something which many of you are seeing for the first time. There were a few, and I hope that my answers have sort of dispelled a few of the doubts, but there should have been many more. I'm guessing there are not that many because people have not yet gotten around to watching that in full. But that will become difficult in the long run, because we are already actually going slower than the pace at which this course is supposed to be administered. And that's understandable, but we can't go much slower than this. Okay? Anyway, questions? Because if there are none, then I'm going to ask questions. None. Right. So it's my turn to ask questions. Fine. So the question that I have for you is related to the next part of the topic, next topic that we are going to talk about. Almost everybody told me that you know about j omega L, 1 by j omega c and everything, right? Is there anybody here who does not know these things? If you don't, and please don't feel embarrassed that everybody else knows. There may be many more who don't know, and they're just keeping mum for the same reason. Since nobody is saying anything, I'm assuming everybody knows this. Okay, does anybody know this? Yes or no? What exactly is SL in the context of? Okay, so that means that most of you don't know what a Laplace transform is. That has not been covered yet. Okay, well, I will just quickly tell you what Laplace transform is today, in which is definitely a huge ask, because Laplace transform is a huge mathematical topic and takes few classes to talk about it. But Laplace transform, the one we will need to know a bit about the Laplace transform in order to understand rest of the classes. Not immediately the next one, because there I'm going to talk about the standard j omega L and 1 by j omega c scenario. But the Laplace transform essentially is something like this. Suppose you have a function of time f of t. If you multiply this by e to the minus st and integrate from 0 to infinity, this thing, okay, it's a function of what? The result? Does the result depend on t any longer? What does the result depend upon? S, right? It's a function of S. So you call this a function of S, and this often written as L of f at S. So L of f, this is a function transform. You had a function f which are transformed into a new function capital F. This stylized L is, of course, the first letter for Laplace. So this is what is called a Laplace transform. Now, most of you must have seen something like this. Suppose I did this. What will this be a function of? Omega, right? And any idea what this is called? This function of omega? Which, let's say I'm writing f tilde. It's a different function, of course. So what is this this thing called? It's called a Fourier transform, right? Many of you know this because you know Fourier series, and I guess I taught you Fourier transform. Did I? I don't remember. Did I teach you Fourier transform?
Yes, sir.
So this is the Fourier transform. Okay. As you can see, the Fourier transform and the Laplace transform are very similar, right? Except that, except for two things. One is, instead of I omega or j omega in the electrical circuit language, you have an S, right? Well, so you might imagine that there's a purely imaginary thing here and a purely real thing here. The second statement is not right. This S actually can be complex. So that way there is no huge difference between this and this, right? But S is complex typically, as you will see, real S, real part of S typically bigger than some positive number. That, well, can you realize why that's being done? Notice that you're integrating all the way up to infinity. So as long as the function of t does not blow up very rapidly, having an e to the minus st term here makes the thing die down fast enough so that the integral exists. Okay. The trouble with the Fourier transform is very often the integral may or may not even exist. The Laplace transform, on the other hand, unless the function is really badly behaved, the integral usually exists. But there's another major difference here. And can anybody tell me what that is? Apart from the fact that you have an I omega for Fourier and S for Laplace. What's the huge difference? In the two cases? This one here and this one here.
One is integrated only on the positive values.
Could you just repeat that a bit further from the microphone? Or integrated only on the positive values? Well, right. More importantly, there is a lower limit, finite lower limit to the integral. Okay. Whereas for Fourier transform, the integral is over the entire real line. For Laplace, as it stands, as we have written it, is the limit is only from 0 to infinity. The real point is Laplace transform is useful when you talk of causal situations. Causal meaning things which start at some time. In this case, we are using the word causal in that technical sense, that we are not talking about a signal which has been there forever. Right? When we say a sinusoidal signal is there on a circuit, we make statements like that, right? You have the AC signal is given by sine omega A, say E is equal to E0 sine omega t plus phi. You should all realize that that's impossible. Why is that the case? Because sine omega t plus phi essentially is a function which will be non-zero or which will be non-trivial over the entire timeline, which means right from minus infinity to plus infinity. What does that mean? It means that the circuit has never been switched on or off. It has been there since the beginning of time. Or if you really want to push it that far, it cannot be even, in that case, if you have a big bang, you don't have a t equal to minus infinity at all. Right? Of course, in real life, you say it has been started so long back that I don't really care. Okay? Now, that's a perfectly good viewpoint to take. If it has been started so long back that I don't really care, then using it to the minus I omega t and the Fourier behavior is fine. However, very often, there are certain crazy things which happen when you just switch on a circuit. Okay. Suppose I just throw the switch, the circuit comes live, and some things happen during that time. Of course, you all should know this, right? Most of the analysis that we have done using this G omega L 1 by G omega C, these are for long times. These are basically for steady state values. Once the value settles down to steady state, J omega L 1 by J omega C, they work fine. Now you might say that typically circuits take very little time at all, say microseconds or milliseconds, or even if it's a second or so, to come to the steady state. So why bother? Why bother about what happens before that? The answer is your circuit must survive till the steady state, right? If the initial surge is so huge that your circuit burns up, then having a nice steady state behavior will be useless. So you very often have to pay attention to what's happening the moment you throw your switch, when you start your circuit. So initial behavior, which stays for a short amount of time and then goes away, these are called transients. And understanding transients is much easier through Laplace transforms, because Laplace transforms essentially deal with functions which start somewhere instead of starting or staying the same from minus infinity onwards. And the real reason why this is so useful is this. If you want to calculate, suppose I have a function which is a derivative of f, and you want to find its Laplace transform. This is what it is going to be, right? You start with the derivative multiplied by e to the minus st dt. Now, the next step should suggest itself immediately. What should you do here? If you have an integral like this,
Integral by parts.
Exactly. You would integrate by parts, right? And you would take f prime t as a second function, the function you integrate. So this becomes f of t e to the minus st, 0 to infinity, right? Minus, and it becomes a plus because of the minus s which comes from the e to the minus st. So can you see what has happened? The first term is what? I'm assuming my function f of t is nice and decent, does not blow up too badly at infinity. And remember, it's the minus st, the s has a positive real part, which means there's a decaying exponential here. So at infinity, this will just blow up, right? Sorry, this will just go to 0 because whatever f of t is, e to the minus st just goes to 0 faster. Okay? So what happens at the lower limit is simply minus f of 0 plus, and what is this thing? S times L of f is the new function, the Fourier transform, sorry, the Laplace transform small f. Notice the differentiation essentially becomes the same as multiplication by s, right? Differentiation in the time domain, differentiating the original function which is a t, ends up becoming multiplication by s, apart from this minus f of 0. Okay. So what good is this? It actually helps you to change differential equations, for example, into algebraic equations, because derivatives in the original equation, which is t, simply becomes multiplication by s. And so it's very often pretty easy to find out the Laplace transform or the solution of a differential equation just by changing the derivatives by this method. So upshot is, because we will deal with a lot of differential equations with the initial conditions, the great thing is the initial condition is also thrown in. So when you change the differential equation into a algebraic equation, the algebraic equation already has the initial values, f of 0. Here, for the second derivative, of course, you'll end up with s squared times the Laplace transform of f minus s times f prime at 0 plus f of 0. So this is something which I will ask you to figure out yourself. Pretty straightforward. The essential idea is differential equations can be converted to algebraic equations, then solved with the initial conditions thrown in. So you want to know what's going to happen at the very beginning of switching on the circuit, which is something we have to pay attention to often. The Laplace transform is the way to go. Okay. So maybe not in the next video, but in the couple of videos after that, we will discuss Laplace transforms and its applications in big detail. But till then, I will ask you to definitely listen to the other videos, the fourth one, which gives you some applications of the two-port networks, and submit your problem sheet. This one, by the way, the 10 questions are very big ones if you try doing everything by hand. But as I told you, you should not try doing everything by hand. You should write down the equations following the standard mesh method or Norton's method or whatever. And then the final calculation, solving the equations, should be done using a computer system. Any computer system will do, but since you already know NumPy, just extend whatever you learned in the last semester and just use numpy.linealg.solve. And that's it. Should be pretty straightforward to work out. Okay. So if there are no further questions, we will wrap up the class now. Okay. No further questions. The class is dismissed. Let me just stop the recording.